We can hear you.
Thank you.
Yes.
All right, let me go over the schedule. There's a slight change in our schedule this week. So today we're going to be doing our test review. So on the link that is provided for today, it's 4 pages, but the test is not going to be that long. It'll be like three pages long, but I'm not going to be able to get through everything. Okay, so I'm going to highlight the problems that I feel are the ones that we haven't seen in the last couple of days. But the ones that I don't get to, I am going to try to cover them in the reviews and the help sessions before and after school. So I'm going to have a help session this afternoon at 4 p.m. Tomorrow is asynchronous day, so I'll have a review at 8:30. Going over the test review, problems that we didn't get to, and then 3:30 p.m. review. They're all going to be recorded on Teams. Okay, so the change is Thursday and Friday. So we're going to switch those days around, and we'll have the test on Friday now. Test is going to be on Friday instead of Thursday. So Friday, we were going to start 3.1 notes. So we're going to start 3.1 notes earlier on Thursday, obviously not on the test. All right. And now I'll have a morning review Thursday and Friday. Thursday morning, 7:15. For those of you who are taking the test here, but can't make it to the 7:15 review, I'll have it for you in the morning, Thursday. And then Friday morning, another 7:15 review. Okay, any questions about schedule for this week? All right, so next week, we're going to offer 2.2, 2.5 recovery up to an 89. And it's either going to be 7 a.m. or 4:15 p.m. on Teams. There's a procedure, details to follow. I am working on trying to finishing grading your test, so I should hopefully have that done by tonight. If I have it done by tonight, I can push out the test to you. So the procedure, I'm going to be working on that as well, so that I can have that all spelled out, so you know all the details involved, and then you can ask questions on Thursday. So some of the procedures and details involved are having to do corrections on the test, doing some additional assignments, turning in your classwork notes for 2.2, 2.5 unit. Okay, so those are a couple of things that are required in order to be eligible to take Chapter 2 recovery test. But again, more details to follow. I'm working on that, and I should have that for you. I'll send you a message either through Teams or through Remind, so you can read through that and just and I can answer any questions you guys have on Thursday. All right, any questions you guys have for this week? Okay, let's go to our test review. And let's do number 1. This is the balloon rising problem, Pythagorean theorem problem. All right, so I'm going to read through this and then set up the problem, and then have us talk about what's different about this compared to previous ones that we've seen. All right, so balloon is rising vertically above a level straight road at a constant rate of 1 foot per second. just when the balloon is 65 feet above the ground. So let me draw that. We have a balloon that is 65 feet above ground. At that moment, we have a bicycle that's going to pass underneath the balloon, right? Moving at a constant rate of 17 feet per second. How fast is the distance between the bicycle and the balloon increasing 3 seconds later? So that's where our hypotenuse for the triangle comes in. So we have x component, y component, and z component. Pythagorean theorem, we know that we're always going to create the same equation, same derivative. It's the information gathering that's the more challenging part. Okay, let's list out all of our variables. So let's go back and read the problem here. A balloon is rising vertically above a level straight road at a constant rate of 1 foot per second. Where can we insert that into? Has to be a rate, right? It has to be time involved. So which one will it be? dx dt, dy dt, or dz dt?
dy dt.
Yeah, good. And the balloon is rising. Well, the rising is not what's causing that positive, right? It's the fact that this part of the triangle is going to be growing, getting larger, longer over time. So that's why we want that rate to be positive. Okay. When the balloon is 65 feet above ground, bicycle moves at a constant rate of 17 feet per second. So where's that 17 going to go? Okay, dx dt. And again, as he's moving away from the passing underneath the balloon, this part of the triangle is also getting longer. So we want that dx dt to be positive. So how fast is the distance between the bicycle and the balloon increasing? So what variables will hold this information? Okay. That's the unknown, right? That's our goal. All right, so far everything feels familiar, right? Okay, so this is the part that we got to be careful about, the 3 seconds later. So let's picture this problem in motion. So at 0 seconds is when the balloon is at 65 feet and the bicycle is sitting right below the balloon. Let's talk about the balloon here. Where's the balloon going to be 3 seconds after this moment? 68. And why do you say 68?
It's 1 feet per second.
Yeah, good. So it doesn't stop moving at 65 feet, right? That's time 0, but after 3 seconds, it's still moving and it's still gaining altitude. So 65 plus 1 feet per second, 3 seconds later will be 68. Yeah. Okay, let's talk about the bike. The bike is sitting below the balloon at time t equals 0. Where is it going to be 3 seconds later? 17 times 3, right? 70 feet per second. We travel at this rate for 3 seconds, we're going to get 17 times 3, 51. All right, so that's the hard part. The hard part is getting to these numbers. After this, Pythagorean theorem for the z, and then plugging in to get the dz dt. Okay, so let's see if we can finish this problem. Okay, let's check our answer. 11 feet per second. You guys get that? Good. All right, any questions with number 1? So I'm going to skip number 2 and 3, but talk about 2 and 3 for a moment. 2a and b, and then 3a and b. Anybody still need to look at number 1? Okay. So linear approximation. We went through this yesterday. Hopefully you guys see this as an easy topic, right? Because most of our work is just getting to that tangent line equation, right? So order pair from the original function. Find the derivative, use the derivative to find the slope, point slope form, and then that's 95% of the work, getting to that tangent line equation. Because the last part is just to plug that decimal in for the x of the equation. Okay. So that goes for a and b. I'm not going to go through it today, but I will cover it in the help sessions, and the key is also available on the website. So if you guys want to work through on your own and see if you're able to get the right answer, check with the key. But as long as you're comfortable with it, then you know you're good. Problems that involve limits would be ones where potentially we got to use L'Hopital's rule. So we talked about how with limits, we always plug in that number, right? Regardless of what you're dealing with, plug in that number to see what you're dealing with. So when you plug in that number, there's 3 options, right? Either you're getting a real number, which if you get a real number, you stop. Or if you get undefined, if you get vertical asymptote, then you also stop. You say limit doesn't exist. But if you see 0 over 0, then this is where our L'Hopital's rule is going to come into play. If we get 0 over 0, we know that there's a hole in the graph, but we know a limit does exist. Old method was factoring, trying to cancel out, reduce. This optional method is L'Hopital's rule, where we can find the derivative as a way of cleaning up the expression, rather than factoring and canceling out. And then after we find the derivative of the numerator and denominator, we're going to reevaluate and see if that will get us down to a real number. So if we plug in, and if we still get 0 over 0, then that gives us the license to do L'Hopital's rule a second time. Okay. And as soon as we do L'Hopital's rule, we're going to re-plug in, and we should be able to get to a real number. Then if it still gives us 0 over 0, then we can do a L'Hopital's rule a third time. Okay, so I'm going to skip 2 and 3, but encourage you guys to work through it on your own or come this afternoon, tomorrow for the help session so I can go through this with you. Okay. So I want us to focus our attention on number 4 because we haven't seen a problem like number 4 yet. It's a cylinder problem. So let me just say that cylinders, the equations look a lot like cones, but it's 10 times easier than cones. Okay, so I want to walk through the problem. I want to show you that it's similar, but similar equation, but I want us to work through the problem. You're going to find that it's easier than cones, and we need to be responsible for this tough problem as well. So I want to go through it. So let's look at number 4 here. Water is leaking out of a cylindrical container at a rate of 5 cubic centimeters per hour. We know we're dealing with volume because the cubic centimeters, the hour is time, so we know it's dV dt. And it's leaking, so we know the water inside the container is going to be decreasing, so negative, right? Okay, container has diameter of 12 and height of 16. Let's draw our container. Here's our cylinder. Diameter 12, height 16. Okay, at what rate is the height changing when the water level, I meant to put water level here, I think I changed it on your key, sorry, on your version. So we're trying to find the rate that the height is changing. So we're looking for dH dt of the water level. When the water level has a height of 3 centimeters. So let me draw in that 3 centimeters, right? So let's say here's the water level here. Let's say that's at height equals 3. Let's put in some related information. Our volume equation looks like this. This is why I say that it kind of resembles cone a little bit, because cone is going to be 1/3 pi r squared h, but the process is going to be a lot different and a lot easier. Okay, so I want to show that to you. The related information is the radius. Okay, what's the radius of our container and the water level?
6.
6. Okay, so I'll put that down. R equals 6. Now, let's picture this problem in motion here. Okay, water is leaking out. Okay, what's happening to the height? Going down, so it's changing, right? It's changing. What about the radius? Stays the same, right? Doesn't matter if it's a full container or whether it's almost empty, that radius is going to stay the same. So this is what's going to cause this to be easier than cones. With cone problems, as water is draining, radius is changing, height is changing. We have to hold on to those 2 variables because we couldn't just get rid of them. And that's why we had to go through similar triangles. We had to create that relationship. So all those steps, we're going to practice it with our next problem, but we don't need it here. So with cylinders, the thing to keep in mind is it's easier because the radius can be replaced. Radius is a constant. So radius of water level is a constant. Okay, it is not changing, so we can replace variable r in the beginning. There's no need to have a variable if it's not going to change for us. So we're going to make a substitution at the very beginning of the problem, and we're going to see our problem get a lot easier because there's no longer two variables to deal with on the right side. So what does our volume equation clean up to be?
36 pi h.
36 pi h. So even at this point, we're ready for our derivative, right? We didn't have to go through the whole substitution and separate equation, deciding whether to solve for r or solve for h. So even at this point, we can just find the derivative. Okay. So we're already cleaned up. We're already ready for our next step. So v becomes, let's find the derivative. V becomes
dv dt.
Good. 36 pi is a coefficient. It's not going to go anywhere. It's just going to stay. And then what's h's derivative? dh dt. Okay. So all we need is dv dt, right? And that can just help us solve for dh dt. So 2-3 steps and we're done. Because the r, the radius is just, it's gone. We didn't have to, we have one less problem to worry about. Okay, divide both sides by 36 pi. Careful, that pi is going to stay in the denominator. All right, and what's our unit of measure?
Centimeters cubed.
No, centimeters squared.
Wait.
Or-
Height though, height. Is
so
it?
it's just centimeters
Good.
per hour.
Right. So the only time we're going to have cubic centimeters or square centimeters is if we're dealing with volume or if we're dealing with surface area or area. So I think I wrote that over here. Where did I put that? Yeah. So the only time we're dealing with square centimeters or square meters or square feet is if you have area or surface area. Okay. The only time you're dealing with cubic is with volume, and that's it. Everything else, it could be perimeter, it could be length, it could be radius, it could be height, it could be x, it could be y. They're all going to be one-dimensional. Yeah. So, centimeters. All right. Any questions here? Okay, take a look at this problem again. What information do we not even need for this problem? Yeah, we didn't need to know the height of the water level, right? It's going to be the same rate. Doesn't matter. It's 3 centimeters. If it's full, if it's empty, almost empty, it's not going to change our rate at all. So careful, right? Sometimes with cylinders, you have additional information that you don't need, and sometimes students want to force it into the problem when it doesn't belong. So just be careful about that. What else do we not need? Oh, you mean the diameter? Yeah. Well, they didn't give us volume, right? So we didn't. But yeah, sorry. What I meant to say was what was given to us that we didn't need.
Oh, is it the
Yeah, the container, right? Now this was important. This will be important if we're trying to do similar triangles, but it's almost like information that's kind of baiting us into trying to put it into a problem when we don't need it. So just be aware of that. All right, there's no similar triangles here. There's no need for it, and also the shape is not conducive for triangles, right? So it's easier, but we got to just be aware that we don't want to get thrown off by information that they provide or that's provided in the problem. Good. Any questions with cylinders? If you need some more help with this type of problem, we can go over some more during the help sessions.
I have a question.
Question?
Yeah. How do you know not to do 16 centimeters minus 3 centimeters when you're using the height in the volume equation?
Oh, you mean over here?
Yeah.
So we don't want to plug in 3 and 16 into this equation because we are still holding on to the fact that h is not constant, right? We want to hold on to that variable. If we replace h with 16 and 3, then we lose the variable. If we lose a variable, there's no way that we can get a dHdt to show up, right? If we find the derivative of this is going to all be a constant, and the derivative of constant is going to be 0. So we're stuck not solving the correct problem. So we're holding on to that h as long as we can. We find the derivative, but when we find the derivative, notice that h disappears. So we didn't have a need for h because it wasn't a variable that we needed to find what we're looking for. And it's because h is only to the first power. With cones, h is going to end up being a higher degree, so there's an h and dHdt that shows up. But here, h to the first power, it's just going to disappear, and it's going to be left with dHdt. There's no h's, so that's why we didn't need that 3. Okay, did that answer your question, or?
Yeah.
Okay. Right, even if we were to use this will not be used until after the derivative anyways. Right. Again, we talked about how the height is changing, so anytime before the derivative is too soon to replace h. But we can replace r because it doesn't matter at the beginning or end of the problem, that radius is not going to be changing. So we can just go ahead and replace that r. Okay, so we got through with this problem. Any other questions? So let's practice the problem that's the most involved, and that's the cone. So let's go to number 7 and let's do the cone problem. See if we can gain more confidence and more comfort with this number 7 here. Okay, so let's read the problem here. We have a cone tank with a height of 40 feet, radius of 30 feet, leaking at a rate of 2 cubic feet per minute. Okay, so that must be dV dt, right? Cubic feet, that's a volume. Minute, that's time, so dV dt. When the height of the water is 30 feet, at what rate is the height of the water changing? So we're looking for dH dt, right? Height of the water is 30 feet. So I need to keep reminding us of this, is that I know it's tempting, but we just cannot use this, okay? Do not use until after your dV dt and your dH dt shows up. If you don't have if you don't have DHDT or DVDT showing up, it's too soon. Okay. We know that there is similar triangles involved because our formula, the shape of the cone causes the radius and the height of the water level to be continually changing. So here's my diagram. Cross multiply. So we know we have to work this equation into our volume equation because we're trying to get it down to one variable, but the decision we have to make is which variable do we want? Do we want this in terms of h, or do we want this all in terms of radius? So our hint is here, right? We're looking for DHDT, so what's the fastest way to get to DHDT? In terms of h, right? H will naturally produce DHDT for us when we go through the derivative. I mean, if you want to solve in terms of r, it'll work. It just takes some additional steps. So I'm just trying to get through this problem as efficiently as possible. So if we want this in terms of h, that means we want the r to be replaced. If we want the r to be replaced, we want to solve for r. So this is where I want you guys to see how much progress you can make from here. So you're going to substitute this in for the r. You're going to clean up the equation. You're going to get it all the way down so that everything is nice and clean. You're ready to find the derivative. But at the same time, you got to keep avoiding this 30. Okay, do not touch this 30. So from here to the cleanup to the derivative is where I think students are having the most trouble. So I want to be able to have you guys try it, and I'll be able to kind of help you guys out if you're getting stuck. Okay, so I'll update the progress along the way, but I'm gonna have you guys try this, see how far you can get from here.
Oh, yeah, I think so.
So 6 is not bad.
Okay.
You just have to be able to draw diagrams.
Okay, I was just confused on like how to set it up.
So dy dt, that distance is
Yeah.
0.
Okay, that makes more sense.
That's good.
Yeah, because I was
dt is a bit negative. Because we're
Okay.
hold it at like distance.
Yeah.
But now it's easy.
okay. Yeah, that makes more sense.
Good, yep. So clean up. Get the exponent to resolve, push all the coefficients together, push the h's together. Good. This is 2748 degrees. 3 over 16. No? 9 over 16. Have you
found the derivative, where did that, how did you get from that 3 to that 3? Oh, you did.
Yeah.
So
So I just have to reduce this.
reduce to 27.8.
3 over 16.
Yeah, good. No, wait, 9 over 16, right?
Yeah, 9 over 16.
And now you're ready to, and then the left side is dv. Good. So, yeah, good. So now you distribute that squared through, and try to push all the numbers together.
Oh, no, we're gonna do that one.
Yeah, we'll do that next.
Okay, then I'll just
Okay.
go with the class.
Good, yeah, and now we're ready to do it together.
Okay, so this is where we need to be before we find the derivative. Check your work. Let me know if you have any questions. Notice that we squared everything inside the parentheses. And then once we square everything, we want to push all the numbers together. So the 9, pi, the 3, and 16, we want all that together under one fraction. You may have it as 9 pi over 48, which is fine, but I cleaned it up down to 3 pi over 16. And then we don't want to find the derivative not until the h's are merged together. So I see some students finding dh dt here, but you don't want to do that till the h's are combined together. So you got to make it h cubed. Once you're here, now you're ready for the derivative. I also see some students trying to plug in the 30 at one of these points, and that's too early. Okay. So after you find the derivative, then you can look at these values and then you can start working them in. All right, questions so far? Okay, let's show the derivative step. Power rule, v becomes dv dt, h cubed becomes 3h squared dh dt. Coefficient stays. And now you see the d over dt shows up. Now that h can be replaced with 30. Okay, any time before this is too early. 30 goes in for h, -2 goes in for dv dt, and now you're just trying to move things around to solve for dh dt. All right, any questions? That's good. Okay, no questions. All right, let's look at number 8. Number 8 is a volume and surface area equation where we got to work into equations or multiple equations, and getting it down to the variable that we're looking for. So let's turn to number 8. So number 8 reads, we have a volume of a cube decreasing at a rate of 10 cubic meters per hour. So we know that's dV dt. And the volume is decreasing, so we want that rate to be negative, so negative 10. How fast is the total surface area decreasing? We know we're looking for movement of surface area, so it must be ds dt that we're looking for. That's the unknown, that's our ultimate goal. When the surface area is 54 square meters. Right. We know that we're going to have to involve both these equations derivatives, so let's go ahead and write those out and see if we can find each of their derivatives. Okay, so spend a minute, see if you can find the derivative for both these equations. Remember, time is going to be underlying each of these or impacting each of these variables. And then we can see how we can use the equations that we have to eventually get to our answer. All right, so walk me through this one here. What's v equals x cubed's derivative? Equals
3x squared dx.
Good. Every variable needs to be impacted by time. Okay, what about s?
ds
dt equals
12x.
yeah dx dt. Good. So this is where we are. We're looking for ds dt, right? But to find ds dt, we need to figure out what x is. We need to figure out what dx dt is. So we don't have x and dx dt, but we have s and dv dt. Maybe these will eventually help us to get to those values. So is this helpful in any way? This 54 square?
Plug it into the surface area equation to find x.
And that x is helpful. Okay, so we'll take this, put it in here. We can solve for x, and that x can be used here. Right, so there's our path. There's our path towards x that we need. Okay, what's our path towards dx dt? Can this information help? Can this negative 10 help?
Yeah, because you plug it into the dv dt equation, and then you plug in the x that you
Yeah, the x that we're going to find is going to go here, and then we have dx dt, and that dx dt can, good, right? So a couple of pieces, right? It's not just a straight substitution. We got to go through some intermediate substitutions to get to where we want. So see if you guys can make progress here. Alex, does that help?
Yeah.
All right, so spend a few minutes, see if you can finish this problem, and then I'll go over it after you guys try it. All right, check your answer. Surface area, that's a two-dimensional unit, right? Focus on the word area, so it's square meters per hour. So we talked about how the surface area can help us get to the x, right? So we use 54 in for s, divide both sides by 6, take the square root, we get x equals 3. So once we have x equals 3, we have a piece that we need. But this is also something that we need to help us get to dx dt, right? Now that we have x, which is 3, we can use the dv dt, -10, plug into our dv dt equation, and then that will help us get to dx dt, which is the last piece that we need as we solve for ds dt. So divide both sides by 27. We get -10/27, so I have my dx dt, I have my x, and both these information is what I need to get to my dx dt. So x gets replaced with 3, dx dt gets replaced with -10/27. Calculator, answer. All right, couple of minutes. Let's see. Can we do number 9? Let's do another Pythagorean theorem problem. Number 9. I can show the diagram and then see if you guys can finish the rest. So we have a jet flying from San Francisco to St. Louis. We have a jet traveling from New Orleans to St. Louis. Pythagorean theorem.
Wait, Mr. Yang, are we supposed to do this problem?
Yeah. Can you guys try number 9?
Didn't we already do this?
I'm sorry?
Didn't we already do this? I think it was on the homework.
Oh, yeah. So if you did it already, then you're good. But I also put it on this review for those who didn't do it or want some extra practice. So if you did it already, then they're good. I do want to point something out about this problem, though. What do we have to watch out for when we come to dx dt and dy dt? What's happening to x as the problem progresses? Shrinking. So we want dx dt to be what? Negative. Yeah, negative. What about y? What's happening to y as the problem progresses? Well, it's going north, but what's happening to that? It's also shrinking as well. So I want to keep emphasizing the direction is not going to guide your sign. It's what's happening to that value over time. In this problem, the way that this problem is drawn, x and y are both decreasing, so we want the rates to be negative, both of them. Yeah, so that's the potential tricky part of this problem. I think everything else is pretty standard. Okay, Pythagorean theorem to find your y. And then dz dt should be a negative value because they're closing in on each other, so that Z is getting shortening at a very fast rate. Okay, confirm your answer matches mine. All right, any questions? So this afternoon, I'll have an afternoon review. Tomorrow morning, 8:30. Tomorrow afternoon, 4 o'clock. Going over this review. I'll record it, and I'm going to try to get the test finished. And also give you guys the procedure and details for next week's recovery process. All right, if there are no questions, hope you guys have a great day. If I don't see you tomorrow, I'll see you guys Thursday. Okay, again, test is Friday. Thursday, we're going to do 3.1. I'm going to put the notes up under Chapter 3 tab. So we'll move on to the next tab for Chapter 3. All right, have a great day, guys.
Have a nice day, Mr. Yang.
Take care.
Thank you.